When I asked him what he's going to talk about tonight, he gave me a one-word answer: trucks. Please welcome David Cebon.
Hey. Thank you very much. Very kind. Yeah, well, I'm mainly going to talk about trucks. I'm going to just give you a little selected bio, since I'm Australian and been living here in the UK for a long time, and I thought that might just be slightly interesting. I have very little bit of interest. So I graduated from Melbourne University in 1980, mechanical engineering. I came over here and did a PhD in Cambridge, and I finished that in 1985. I became an hold on, that's not really the right thing. So let's go right back to where we were. I became an assistant lecturer in 1985. I was going to stay here for 3 years, and I'm still stuck here. I became a member of the Institution of Engineers Australia in 1987. And in 1995, they made it really hard to stay a member for some reason, which I don't. That changed the structure, made it expensive. It got really difficult. So I quit the Institute of Engineers Australia. So I haven't been an Australian engineer for 30 years. I started up a thing called the Cambridge Vehicle Dynamics Consortium in 1993. And that was a research consortium with a whole bunch of different companies in the heavy vehicle industry. And that's still going. So that's been running for more than for 30 years. And that's the same consortium, research consortium. They fund my research. And that's been a very fruitful thing to do, to have close contacts with industry supporting the research activity all that time. Something that's not on that bit of bio, in 1994, I span out a company out of the university. It's called Granta Design, and I was the CEO of that from 1994 to 2019, when it was acquired by a company that some of you will know called ANSYS, which is a simulation finite element, and the original ANSYS software is finite element code for mechanical and structural simulation. They bought a company called Fluent, so they do fluids and all kinds of other physics, electrical, magnetic, quantum mechanics, optical, whole range of physics. And our company, Granta Design, was purchased to provide the materials, a materials data system and materials data management product for the company. So that was 2019. Managed to pay off my Barclay card, so that was good. And in 2012, I started a thing called the Centre for Sustainable Road Freight, which was a bit of a combination of this Vehicle Dynamics Consortium, which was a whole bunch of companies like Volvo Trucks and Goodyear Tires and companies that make trucks. And in the Centre for Sustainable Road Freight brought in a whole logistics side to that, and brought in a whole lot of logistics companies like Waitrose and Tesco and DHL and UPS and Wincanton and so on. So a bunch of companies that use trucks. So this was about building better trucks, and this is about using them in a more sustainable way. So that's kind of been my trajectory. I'm still going, but my out to pasture date is 2026. So I'm nearly done after all of those years. So what I'm going to talk about, give a little bit of background on road freight. I'm going to talk a little bit about urban delivery, some options for long haul freight. Long haul freight is where the real challenges are. Talk about some electrification things and draw some conclusions. So that's where we're going. In the UK, a few years ago now, the government announced that it was going to ban the sale of all new petrol and diesel trucks by 2040. So that kind of fired the starting gun. We started looking into sustainable road freight, of course, a long time before this, but in a way for the industry, that 2040 date now has been, at least until the current government changes its mind, that date is fairly well set. And so the industry has to work out how to run road freight without running diesel or petrol engines. So a little bit of background. This is the UK, emissions in the UK. Transport is a quarter, this chunk down here. Slightly out of date, but of transport, cars and taxis 60%, and the area that I'm interested in is light vans and heavy goods vehicles and so on. It's about 30%. It is about 7% of UK's total emissions, so it's a significant chunk. It's about 7 or 8% of world emissions, actually, road freight. So that's similar in scale to the steel industry, and it's about 3 times as big as the aviation industry. So that gives you a sort of a 3 or 4 times bigger than the aviation industry. So gives you a bit of perspective. A few other facts which are interesting. It's about 7% of all UK jobs, 2.3 million people in 200,000 companies in the UK work in logistics. That's quite a lot. And the net return on investment, profit margin is about 1 to 3%. So you'd be way better investing your money in almost anything else other than road freight. And other thing that's interesting, 55% of UK road truck drivers are owner operators. They drive their own truck. So a large proportion of this industry is really well distributed. It's not DHL and Waitrose. It's thousands, hundreds of thousands of truck drivers driving their own trucks. So where do you start with decarbonisation? Well, I can give you a couple of days of talks on low-hanging fruit that you might want to be interested in, and they're things like better tires, low rolling resistance tires, better aerodynamics. Light weighting is very important. The weight of the truck is a really big part of the fuel that it uses, because every time you take off, you have to put that kinetic energy in. Every time you put your foot on the brakes, you dump it all out. So if you're heavier, you use more fuel. Driver performance is quite an issue. The difference between a good driver and a bad driver is 10 or 15% of fuel consumption. Depends on the road. And higher capacity vehicles is something I'm very interested in, something which is Australia absolutely excels in. That ability to have a road train, which is highly productive, much lower emissions per ton kilometre of freight than a smaller truck. And Australia is really the place in the world that has those high capacity vehicles sorted out. So that's been great. There's also logistics things you can do, of course. You can do things like, in logistics, to reduce fuel consumption, what you're really always trying to do is improve the vehicle fill. And you can do that in all kinds of ways. Assuming that you've not reduced demand. One of the things you can do, of course, is reduce demand one way or another. And there's all kinds of ways you can do that. But if you haven't been able to reduce demand, then what you want to do is have a vehicle full and not running around empty. Empty running is really is wasted fuel. Now, there's lots of times when you can't avoid it. A fuel tanker which goes from a refinery to a petrol station and back again, it's not taking a load back to the refinery. It just doesn't. It's a one-way trip. So there's plenty of places where the backhaul is empty. But there's other kinds of things you can do, like collaborate between 2 companies, and one can bring home a load for the other in the opposite direction. There's all kinds of all kinds of things you can do. My cousin used to live in Brisbane. Well, somewhere up the coast of Queensland, and he used to say we see trucks going from Brisbane to Townsville carrying bananas, and trucks going from Townsville to Brisbane carrying bananas, and you have to wonder. So there are things you can do in the logistics. You can relax time constraints. You can collaborate between companies. There's all kinds of stuff you can do. But these things are not sufficient to get to near zero. They're not going to get the logistics industry to near zero emissions. And actually, you have to change the energy source to get near to zero. They are all very important. And as logistics gets more difficult, and particularly with electrification, it's really important to maximize the range of the vehicle, to minimize the amount of energy it uses. And these things are all the more important in an electric world. The options for changing the energy source are electricity, biofuels of one kind or another, and hydrogen. Biofuels I'll just talk about very briefly. The problem, biofuels come in a few different varieties. Some are easier to use than others. Some require new vehicle technology. Some you can drop in. For example, you can have biodiesel made from vegetable oil, and you can drop that in. The problem with biofuels really is that there's just not enough of it to go around. That's the basic bottom line. You can decarbonize, a few individual operations, but you can't. There's nothing like enough for everybody, and so it's therefore not really a viable solution. What we have to do, get the whole industry to zero. So biofuel kind of rules itself out from availability purposes. The biofuel that we've got, and there's quite a lot of it, needs to be reserved for things which essentially can't be electrified, and that would be particularly shipping, long-haul shipping and aviation. So any biofuels we've got need to go into those sectors. There's not enough to do trucking. There is enough to make an impact on aviation or shipping, or a bit of both. So I'm going to talk a little bit about hydrogen, not very much, and you'll discover that I'm not a great fan of hydrogen. I'm going to talk mainly about electrification. So if we think about trying to electrify a system like in the UK, the UK's road network is conceptually pretty simple. There's a sort of backbone of what's called the strategic road network, the motorways and A roads, and hanging off of those, and along those, you'll see, if you go to places like in the middle of the country, in the Midlands, like Milton Keynes or Daventry or somewhere like that, you'll see thousands of warehouses, these great big warehouses with John Lewis trucks going in and out, or Tesco or something like that. And they are national or regional DCs, distribution centres. So a very large part of the country's freight goes through those places, goes up and down the strategic road network between those places, and then goes from those places sometimes to local and regional distribution centres, maybe a thing called an urban consolidation centre on the edge of a town, where you consolidate lots of freight and then take it into the city in a smaller number of vehicles, smaller vehicles. Once you get into the city, and the cities tend to hang off the end of this, you can do everything easily by electric vehicle. You can do parcel delivery, home delivery, sort of multi-drop from supermarkets or whatever on batteries. You charge up the batteries at the supermarket. You do 150 kilometres around the city, multi-dropping. It's a straightforward thing to do. You charge up overnight. And this is happening all over the place. Similar kind of thing. You can come from the edge of town, drop at Tesco Direct, convenience stores, or those kinds of city centre drops. Again, you can do those on batteries. You can do refuse collection on batteries. We're seeing that increasingly, same kind of deal. In fact, anything that's got lots of stopping and starting batteries are great because you can capture the energy from stopping you can recuperate that energy and put it back, or some of it, most of it, put it back in the battery again. So stopping and starting is less of a penalty. This is all rolling out now. It's rolling out through London. It's rolling out through all cities in the country. It's building technologies and supply chains for higher capacity battery electric vehicles. And we'll look back in 10 years' time. Everything in cities will be electric buses as well. Everything will be electric. We'll look back and say, well, why do we ever have those smelly diesel trucks driving around, creating noise and pollution and so on. So cities are going electric now, and that's a done deal as far as I can see. What about the long haul? How do you do the long haul? If we've got the cities worked out, how do we do the long haul? And that is more of an issue. The long haul, of course, in the UK is not that long, but it's long enough to be a challenge. It's not like driving across the Nullarbor or, north to south up the Stuart Highway. It's still, it's a challenging thing to do. So when we think about electrification of the long haul, the government, the UK government, thinks that the answer is charging in truck stops. You just dump a bunch of chargers into truck stop, motorway services area or something like that, and you're done. So that's one sort of thing you could do. Charging in truck stops looks something like that. Another thing you could do is that you could charge in logistics facilities, and those warehouses that I mentioned, like in Milton Keynes, they look like that. You've seen them. And they almost all have diesel filling capabilities, local diesel filling capabilities. You'll never see a Waitrose truck in the motorway services because they always fill up in Waitrose facility as part of their normal operations. So that's interesting because this solution assumes they're going to fill up in the motorway services, and they don't. That's not what they do. So you can charge at the distribution centres, you can charge at other logistics facilities, factories, and so on. That's going to look something like this, with trucks quite likely on charge while they're on the loading bay. So there's a bit of a challenge there. There is another possibility, and it looks something like this, and it's what you call dynamic charging. There's a couple of versions of this which are viable. This is one. This is a system in Germany, which has got overhead contact lines like a railway line, and a pantograph on the truck, which goes up to the railway, up to the overhead contact lines, and it collects about 300 kilowatts from the overhead contact lines, and about 150 kilowatts is needed to drive the truck, and about 150 kilowatts is left over to charge the battery. So that's quite interesting, because when you get to the end of the line, you drop the pantograph, and it's got a battery on board, and you drive on the battery to your distribution center or warehouse or whatever it is, and load and unload, unload and load, and come back to the motorway network, put up your pantograph and charge as you go, as you drive. That obviously has a bunch of advantages. The first is you didn't have to stop and charge at the distribution center, and that's significant. I'll talk about that a bit later. The second is that you only needed a very small battery to get from the motorway to where you were going and come back again. And that means that you can have a truck with a small battery, a little bit of hardware on the top, which is pretty lightweight, and it means that you can easily carry a full load. This truck can be completely loaded and carry as much as a diesel truck. So that's a couple of very significant logistics advantages. You don't have to carry a big heavy battery, only a small battery. And when I say small battery, you're talking about 150 or 200 kilowatt hour battery, right? Tesla is about 80 kilowatt hours, so it's not that big compared to a big battery solution is about 600 kilowatt hours of battery. So you carry about a third of the size of battery. So that's one possibility. There's another possibility, and I haven't got a decent photo of this, but this is a contact line actually in the road down the middle of the lane. And it's like a Scalextric arrangement. You have a contact which goes down, or a couple of contacts go down to a strip which is flush with the road surface up the middle of the lane. And as you go along, you draw power from conductive rail in the road. And that sort of technology is used quite a lot in Europe for trams. And it can be used for city centre buses, but it also can be used for charging and powering trucks and cars, in fact, on the motorway. So that's a very interesting technology, which is pretty new, but is very interesting. So these are all possibilities for charging trucks in the long haul. Now, I said I would say a little bit about hydrogen. I'll have a bit of a detour to hydrogen for a minute and a few numbers. So here is what happens if you start with 100 kilowatt hours of renewable electricity and you want to drive a battery electric vehicle. So we've got 100 kilowatt hours that comes out of a wind turbine, solar panels, nuclear power station, whatever, hydroelectric, whatever is your flavor of renewables. You transmit it via the electricity grid and you've got some losses, maybe 10% losses in the UK, that's the average. So you've got about 90 kilowatt hours by the time it gets to the end user. You've got to put that into a battery and then it comes out of the battery again. And that is slightly lossy. You lose about 15% on the round trip through the internal resistance of the battery. That gives you about 77 kilowatt hours left. And you put that into your drivetrain of your battery electric vehicle, which is about 90% efficient. And now you've got 70 kilowatt hours getting to the wheels of the truck. So you've lost 30% of the electricity between wind turbine to wheel. And that's not too bad, 70% efficient. That applies to any battery electric vehicle. You know, that's not just a truck, that's a car, that's your Tesla, does the same. That is a battery electric ferry, a scooter, a bike, a battery electric airplane if you had one. That's the, you know, you can expect to get 70% of the electricity to the wheels, to propulsion. Now, if you choose instead to make hydrogen, you can take your 100 kilowatt hours, you've got to convert it to DC from AC, and you put in an electrolyzer. Now, the best electrolyzers are about 75% efficient. So by the time you get out of your electrolyzer, you've got 71 kilowatt hours of hydrogen, green hydrogen's called. You can take your green hydrogen, you can, compress it, transport it, you know, compress it, put it in a tank, transport it, decompress it, put it through a fuel cell, and it goes from being green hydrogen back to being electricity again, the yellow electricity. And the problem with this is a fuel cell is about 50% efficient. And no fuel cells are any more efficient than that. And the reason for that is that they have to satisfy the second law of thermodynamics, which we all learned about at undergraduate mechanical engineering school. And there are also kinetic constraints. And so that means that they're really constrained, just like a diesel engine is constrained or a petrol engine is constrained to have an efficiency of 30 or 40%. Fuel cell is not going to do any better than 50%. So, and that's because the problem here is that we're taking electricity, which is what we call work, we're turning it into hydrogen, which is a chemical fuel, which is considered to be thermodynamic heat. And when you convert heat back to work, you suffer the second law, and there's a maximum efficiency you can get, and that's about 50% in the case of a fuel cell. So we're now at 26 kilowatt hours. We put that into our 90% efficient electric vehicle, and we've got 23 kilowatt hours of propulsion. So we've thrown away 77 kilowatt hours of electricity. We've got a 23% efficient windmill to wheel process. And that's a problem. The third one, which is the electric road, which I showed you, the overhead contact lines or the strips in the road. Its big advantage actually is that you don't have to go through in and out of the battery. And so when you're not going in and out of the battery, when you're going directly transmitting from the overhead contact lines into the vehicle, you're at, well, you don't have this the battery in and out of the battery problem, and you get about 77 kilowatt hours at the wheel. So that is the most efficient way you can do an electric vehicle. Pretty much the most efficient way you can do any vehicle. So if you just get that electricity to the vehicle in wires instead of in a box, you try and put it in a box and carry it, it's very difficult with electricity. But if you can transmit it down wires, which is what electricity likes to do, you can get that really high efficiency, 77%, quite low losses from windmill to wheel. That's sometimes called ERS, electric road system, or dynamic charging. Now, it's interesting to think through, and I'm just going to show you a comparison of this one and this one, the most efficient and the least efficient, to just give you an idea of what the implications of this are. Because we often hear, those engineers, they keep talking about efficiency, but there's all sorts of other things that matter other than efficiency. Now, I can tell you what else matters: cost. It's cost that matters, because we're in an industry which is 1% to 3% profit margin, right? So we're not going to be spending much more than we do now on this system, whatever it is. So let's think about cost. Now, the problem here is this. Suppose that was 25, because it's an easier number, 25%, 1/4. If you wanted 10 units of electricity here, you would have to supply 40 units of electricity there, right? Because the efficiency is 25%. So 40 times 25% gives you 10. If you wanted to do the same over here, you wanted 10 units of electricity at the bottom, you would have to put in about 1.14 units of electricity at the top. This function is hyperbolic, right? We're divided by the efficiency, and when you divide by a very low number, you get a very big number. So the basic problem here is, the basic fact of the matter is, if you know how much electricity you need at the bottom, you can work out how much you need at the top. And the lower the efficiency, the worse that comes out by a long way. So this is how this plays out. Here's a map of the UK. Let's assume that we had to generate the electricity to power all the trucks in the country with onshore wind. Now, it wouldn't ever be onshore wind, but it's useful to show that. It could be offshore wind, it could be solar, hydro, nuclear. Let's just assume it's onshore wind for now. If we wanted to power all the trucks in the country using the ERS system, the overhead contact lines, at 77% efficient, we would need 11 gigawatts of onshore wind capacity. And that would take that's the actual area of land it would take, 5,300 square kilometres. So you have to have that much wind in order to power the UK's trucks, that much wind turbines. It's a hell of a lot, 3,500 big wind turbines, and it takes that area. If you want to do it by hydrogen, it looks like that. Now you need 3.3 times more. You need 36 gigawatts of power. The UK's average power consumption on any day, and it's about the power consumption today, is 31 gigawatts averaged over the day. So we're talking about doubling the capacity of the country in terms of power flow in order to generate enough green hydrogen And the reason we need all that green hydrogen is because we're going to lose 77% of it in losses, in thermodynamic losses through the process. So, oops, wrong one. So here's the thing. This is 3 times bigger than that. Actually, it's 3.3 times bigger than that. It's the ratio of the efficiencies. You need 3.3 times more power for the hydrogen system. You need 3.3 times more land. You need 3.3 times more wind turbines. You need 3.3 times more electrical connections. You need 3.3 times more maintenance men and maintenance people, spare parts, vehicles. You need 3.3 times more stuff. It is going to cost 3.3 times more on average. Now, price of electricity goes up and down, but overall, it's 3.3 times the resources that you need to power that hydrogen-powered set of vehicles. So the operating costs, at least of the energy part, the energy that you have to buy to pay for running those hydrogen-powered vehicles will be 3.3 times higher than for the electric vehicles. There's another thing about hydrogen-powered vehicles is they cost double as much as electric vehicles. If you actually go out and buy one, try and buy one, and I've had to try to buy one recently for a research project, a big research project funded by the government. What you have to do is purchase a whole bunch of vehicles and run them for 5 years and show how it all works. That's a demonstration trial. Try and buy electric vehicles, they cost about 300,000 quid a shot. Diesel is about 150. So an electric truck is about twice the cost of a diesel at the moment. Try and buy a hydrogen powered truck, costs 600,000 pounds today if you want to go and buy it. So double the cost of the electric vehicle. Now we think, well, what's going to happen? What will happen to the prices? You know, these prices are going to go down, right? They're all going to go down. We're going to make lots of stuff. We've got learning curves. We've got huge, improvements in technology with time. Just look at wind turbines and solar panels. Hydrogen fuel cells are going to get cheap, right? Well, they're not. Well, they might get cheap, but they're not going to get cheaper than battery electric vehicles. Why not? If you think about the battery electric vehicle and the hydrogen vehicle, they're both basically electric vehicles. They've both got, all the bits of a truck, wheels and frame rails and cab and all that. They've both got electric drives. They've both got batteries and inverters, electric drives. The hydrogen fuel cell truck has a fairly small battery, Tesla-sized battery. The battery electric truck has a big fat battery. It's got 600 kilowatt battery or something like that. It's a kilowatt hour battery. So the difference between these two vehicles, one has a bigger battery, the other has hydrogen delivery and charging equipment, hydrogen storage tanks, and hydrogen fuel cells. Well, the delivery and charging, all that equipment has to carry the leakiest molecule, the leakiest element in the universe. I often hear people say, hydrogen's the most abundant element in the universe. Well, it may or may not be the most abundant element in the universe. It's not actually accessible because most of it's in stars or in water, but it is definitely the most leaky element in the universe. There's no doubt about that. It leaks through everything. So you need high-tech seals and high expensive materials, tight tolerances, very fancy engineering, safety critical, high pressure. You need fuel cells that are full of platinum and iridium and catalysts and so on. Overall, that fuel cell bit is why the hydrogen truck currently costs double the battery electric truck. Now we think about what's going to go down in price quicker. The battery electric truck is made by is developed by the automotive industry. The entire automotive industry in the world is trying to bring down the cost of those batteries. Every single car company, except for one or two very minor exceptions, has huge and all kinds of other companies working on reducing size and cost and improving the power density of batteries. One thing we can be absolutely sure of, batteries are going to get cheaper and cheaper and better fast as possible. How many companies are working on fuel cells? You've got 1,000 engineers work in the world working on fuel cells, compared to hundreds of thousands or millions of engineers and companies. And so there's nothing surer than the fact that batteries are going to develop quicker and more effectively than fuel cells. And so the price of electric vehicles is going to come down much more quickly than the price of hydrogen fuel cell vehicles. Hydrogen fuel cells are currently twice the capital cost of battery electric vehicles. They will always be significantly more expensive than battery electric vehicles, probably always more than twice. So the only reason that you would drive a hydrogen-powered truck is if you really couldn't do what you needed to do in a battery electric truck. That's the only reason. There's no way you're going to sell these things to fleet operators with 1% to 3% profit margin unless they're getting a hell of a lot of something for that double capital cost and 3 times operating cost. The 3 times operating cost is governed by the laws of thermodynamics. It's not, I didn't make it up. It's that previous graph, it's the laws of thermodynamics. So hydrogen is too expensive. It is not going to be, we will not see hydrogen powered trucking taking over the world. It will have to be electric. And when you look at electric vehicles, it's interesting to think about the compromises here. I've mentioned the electric road system, which I think is a very interesting thing. If you imagine having an electric road, then suppose this is the electric road network, on the main roads in the country, the heavily trafficked roads, and it needs to be the heavily trafficked roads because that's where you've got lots of trucks going past and you can sell them electricity. And by selling electricity, you can pay for your infrastructure. So you need lots of trucks. So these are the heavily trafficked roads in the UK. When you get out to the wilds of Scotland like that, you are not going to be able to afford to put your infrastructure along the highway anymore because there's not enough trucks. And so you're going to have a range of battery-powered operation out there in the wilds. And in fact, you're going to have them in lots of places in the country where you have to just operate on batteries. So you're going to have some big batteries in your trucks. And you're going to have static chargers out in those places where you can charge. So you're inevitably going to have a combination of electric road system and some big battery operations. And the interesting question is, how much of each do you have? You see, if you have a short electric road network, if you have a small network or zero network, then what that means is that you need lots more static chargers, and 200,000 trucks need much bigger batteries. If you make your electric road network bigger, then you need a lot less static charging, and all those 200,000 trucks can have smaller batteries. And so there's somewhere in the middle of that, between zero electric road network and huge electric road network, there is an optimum point. We don't know exactly where it is. It's quite hard to work that out. But it's interesting to see what happens as you approach that. So here are 3 different networks. This is what we call a light network, and it's just, the M25 here, the M1, the M4, M6, and A14 going across from Ipswich across the country and so on. And as you go across, you get more and more of the electric road network and lots of static chargers dotted around. So what happens when you do this? Well, you can simulate a truck. And here's a simulation of a truck. This is the speed profile is in black. The elevation profile is in red. Going up and down hills, you need to take that into account. Take the speed into account. 100 kilometers an hour on cruise control here, 90 kilometers an hour and so on. And this is the state of charge of the battery. And so the battery starts off full and it goes down, and then you charge up at this spot here. There's a rest stop here, and battery's charged up, and then down we go again. We drop off a load here, and the battery state of charge stays constant, and then goes down again, and we charge up it again at another rest stop, and so on. So we can model all this stuff, and we can do it with a fair bit of confidence. So what happens if we look at some real journeys? So this is a real journey. This is a company we called Operator H, and this is 18 hours in the life of one of their trucks. So the truck starts off down here, goes out to the west and comes back again, goes down the south, down to the Isle of Wight there, and goes back again, comes all the way up around the M25 over to Chelmsford here, and then comes all the way back again, and that finishes its 18 hours, two drivers, and stops for the night. So if you were to do that whole thing by charging up the vehicle in the depot, big battery, like you would with the diesel truck, you fill up a big battery and drive it all for that 18 hours, you would use 1,666 kilowatt hours of electricity, 1.7 megawatt hour battery. Now, that is never going to happen. The biggest battery you can get on any truck is 600 kilowatt hours. So 1.7 megawatt hours is just not going to be a thing. So that's not going to work. So how are we going to do it? Well, we can charge in different places. We can charge at the drop-off sites. There's 3 of them, right, where you drop off the load. And if you do that, and if you charge for the amount of time that this vehicle actually spends at those locations, you charge at 600 kilowatts, which is a plausible number for a fast charger for a truck. We're expecting to see them up to about a megawatt or more. So 600 kilowatts is right in the range that we expect. If you charge it at 600 kilowatts, you need a battery size of 397, 400 kilowatt hours, which is plausible. You can get a battery on a truck, which is that. If you charge at the public rest stops, and there are 2 public rest stops where this driver has to stop after 4.5 hours statutory rest break, have to stop. If you charge at those locations only, you need an 800 kilowatt hour battery, which is too big, at least for now. That's too big. And if you charge at both the drop-off points and the rest stops, it's about the same. The reasons are that most of the power is needed around this bit. Now, if you have the light ERS, this is what happens. The blue lines here are where the ERS lives, and you can see the light one, only part of the journey that covers it is actually the M25 around here. But if you do that, the battery size, if you don't do any other charging, comes down to a megawatt hour. If you charge at the drop-off points, now you're at 240 kilowatt hours, and that's the size of a battery in a bus. So that's a plausible size. If you charge at the rest stops, public rest stops, you're back at 800 kilowatt hours. You need that all around this bit. And if you stop at both the rest stops and the drop-off points, you're down to about 240. It's about the same. But this is a hell of a lot better. And as you go to more ERS, this is what happens. And there is the medium and the heavy ERS. You can see that we get down to batteries which are of Tesla size. So you only need really rather small batteries on the truck. Less than these green ones, the total weight of the batteries is less than the diesel powertrain. So you can carry more on these electric trucks, which you're charging on the network, than you could carry with your diesel. So what happens is that the more ERS you have, the smaller the batteries you need, and that's a key thing. So if you plot a bit of a distribution of lots and lots of journeys, you get this sort of a picture. The blue here is with no ERS. You can see it coming out to 1.4, 1.5 megawatt hour batteries under some circumstances, with a mean of 600 kilowatt hours. And with the ERS, the whole distribution comes down here. The mean is 300 kilowatt hours, but and most vehicles are less than 600. So that's a much more plausible situation. If you have destination charging as well, charging at the warehouses, then this all pulls it down much further. And now we're down at 150 kilowatt hour batteries. So that combination of warehouse charging and ERS means you can have very small batteries. So if we look at the cost of all of this, this is the cost of ownership of the truck. So what we're looking at here is a 6-year first life of a truck. You typically buy a truck, you run it for 6 years, and you sell it to somebody else. So you pay the capital cost, you pay the running cost, and you recoup whatever it's worth at the end of life. If you do that with a diesel truck now, the cost is about £400,000 over the time. You use about £40,000 a year in fuel, and it costs $150 to start with, and then you get some money back. And we don't know what's going to happen to the price of fuel or diesel trucks over the period from 2030 to 2050. And our best guess is the price of diesel will be constant. Who knows? It could plummet as demand disappears. It could go sky high as it becomes very rare. We really don't know what's going to happen to the price of diesel. So we're just assuming it's constant. If we look, we can make estimates of what will happen to the price of battery electric vehicles and hydrogen vehicles. This is a hydrogen-powered fuel cell vehicle. You can see that it starts off significantly more expensive in its total cost of ownership than the diesel. But it's going to get cheaper over time as a fuel cell gets cheaper and maybe hydrogen costs get less. That's our best estimate of it. This is a battery electric vehicle with a 1.2 megawatt hour battery. You can see that it never catches up with diesel, with the price of diesel. But as you go to smaller batteries, there's a 500 kilowatt hour battery, 300, 150 kilowatt hour battery. You can see that it's cheaper. It will be cheaper if we had electric road system to run that 150 kilowatt hour battery cheaper from 2030 onwards. The important thing here is that if trucking is more expensive than diesel, because the companies are not able to carry any more cost because their profit margin is so crappy, this all has to be subsidy. The only way you can run vehicles that are more expensive is for the government to permanently subsidize the cost of the fuel. On the other hand, if you can run these vehicles more cheaply than diesels, then you've got the opportunity for tax collection, headroom for tax collection. That's important because diesel excise duty is a big chunk of the money that governments get into their tax pool. And if you can have more efficient vehicles, which is what this is about very efficient electric vehicles with small batteries that don't use much energy, then you've got headroom. You're creating headroom for tax from the efficiencies of the extra efficiencies of the vehicles. So that is a big plus. So I've just conclude. Hydrogen is always going to be too expensive. Twice the capex, 3 times the opex. It's just never going to fly. Battery electric vehicles are available now. They do have a significant payload loss. I can talk about that because of battery weights. But it's still the only way to go, really. If we had some weights and dimensions changes, you could get back to 44 tons, which is the gross weight capable for a diesel vehicle. Yeah. We've got megawatt charging standard coming soon. That's going to allow us to charge fast. Electric logistics is doable. You know, I came down to the conclusion that the only reason you would buy hydrogen vehicles is if you couldn't do the logistics you need to do. I think we showed with that little case study that if you have get the charging right, you can do the same electrics pretty much, but you need to get that charging infrastructure into the right locations. Charging is the challenge. Truck stop charging is necessary, but by no means sufficient. The government thinks all it needs to do is put chargers in truck stops. It's not going to work. Warehouse charging is essential. And warehouse charging is a problem because it takes a lot of power. You've got lots of warehouses in the country, about 30,000 of them, and they all need big, fat electric connections if they're going to charge trucks. That is a distributed problem. It's a big problem for the electric supply industry, and that is one of the real difficulties with electric trucking. So electric supply to warehouses is very challenging. It's a major infrastructure issue. And so that is why straight battery electric vehicles are going to be very challenging. Not as bad as hydrogen, but still challenging. The combination of battery electric plus ERS is the lowest cost, the lowest carbon, the lowest weight. It reduces battery size and cost by a factor of 2 or even 4. It eliminates the loss of payload on the heaviest trucks, gives headroom for fuel recovery, and eliminates most static charging and thousands of warehouse grid connections. So, and you can use it for aviation as well. There we are. That's the end.
No, thank you very much. I think we've learned quite a lot about buying trucks with new energy, and hopefully we can avoid any alternative facts. We're armed if other people come to try to push some alternative means in the future. Does anybody have any questions?
Yeah.
Thanks. That's absolutely fantastic talk. Very, very much. Really enjoyed it. Sorry, just looking back in the passage of time, must have been about 14 years ago when I went to a presentation at the Institution of Mechanical Engineers in Birkirk Hall, and it was all about how the hydrogen infrastructure was going to come into the UK with the transportation network. And they talked about this super hydrogen grid that would be built, and you could just pull in and fill up your vehicle and so on. And anyway, I gave a timeline of how it would all happen. And it was quite fascinating because I did quite a lot of research after on power generation in relation to using hydrogen, and all sorts of discoveries about things with the kinetics of hydrogen flames, NOx with when burning hydrogen, all the problems that had, not having the materials, as you mentioned earlier, hydrogen embrittlement. And this seems so much more realistic, because I was just thinking, all of that talk, it was really interesting, and it's all come to absolutely nothing.
That's right.
So thank you very much. Very good talk.
Thank you. Well, that's great. I mean, I can give you a whole other talk on hydrogen. So you gather that I've spent a bit of time thinking about hydrogen. Let me give you one stat, which is an interesting one. If you were to fill up refueling stations with hydrogen, and if you had to deliver the same amount of energy to the transportation, to vehicles as now, you would use, that hydrogen grid isn't going to work. The pipes, refueling stations do not have gas pipes. That's right. So you have to build gas pipes to all the refueling stations. That's not going to happen. So you take it there in tankers. Now, each tanker, they use tube trailers with 700 bar tanks to carry hydrogen. So it's an interesting question to ask is, how many tube trailers at 44 tons do you need to replace every tank of diesel, right? Every diesel tanker. So we've got one diesel tanker, drives up, you use that all day long in the petrol station. How many hydrogen tankers would you need at 700 bar carbon fiber tanks, million quid vehicles? The answer is 18. So you need 18 trucks for every one that's carrying diesel. You need 18. So all day long, every half an hour, you've got another tube trailer going into each of your in each of your petrol stations, or maybe we use them across another bore. Let's just have 18 times as many road trains, 150-meter road trains pulling diesel that go across the wilds of Australia. Replace that with everyone with 18 vehicles. That is really, so just that one thing, how do you get hydrogen to filling stations? It's essentially impossible.
Like that, one of the delusions that was going on when they talked about using, and it doesn't work, without hydrogen blending with natural gas.
Yep.
And I have an interest in metallurgy and finding out exactly what hydrogen does with embrittlement, with pipework.
Yep.
And it just doesn't work because it's just a small molecule, it just gets everywhere. And also the other thing with large gas turbine combined cycle plants, the actual materials to be able to handle those temperatures, they just don't exist.
Yeah, well, it's the embrittlement is a real problem because part of the story is that we'll use the existing gas network. If you look at that, there was a recent study done in Germany looking at how much would you have to derate the pressure of gas pipes in order to keep them safe because of the embrittlement problem. The answer is you have to run them at about a third of the pressure that they currently run at. Now, with hydrogen, you have to, because the calorific value is a third of methane, you have to pump 3 times more of it. So actually you have to boost the pressure and pump it at a much higher pressure. But because of the embrittlement, you have to pump it at a third of the pressure. So you're something like your gas pipeline's capacity is about a tenth, a third of a third, about a tenth. So the idea of using the existing gas pipes is completely crazy. You've got to have 10 times the amount of, if you use the same current materials. So that is another, so pumping it around is a problem, storing it is a problem, burning it keeping it in place is a problem, stopping it from blowing up is a problem. It has a much bigger flammability range, much bigger range of concentrations than natural gas. So it is really a problem. And in fact, the UK government has had a plan to run a hydrogen village trial.
Oh, yes. It all came
to nothing. There were two possible places: Whitby at Ellesmere Port and Redcar in up north near Newcastle up there. Both came to nothing. In fact, in the end, the residents revolted and said, "You're not going to do this to us." The government was forced to step back. So that's all in tatters. Thank goodness, because when you look at heating with hydrogen compared to a heat pump, electric heat pump, you do that same calculation. I've done it, the calculation with the areas of wind turbines. Well, it's not a factor of 3, it's a factor of 6, because your heat pump gives you a factor of 3 improvement because of its coefficient of performance. And so for every electron you get, every kilowatt hour of electricity, you get 3 kilowatt hours out of your heat pump. Or the kilowatt hour of electricity, you turn it to hydrogen and pump it, and you end up with a half a kilowatt hour. So the ratio between 3 and a half is 6. So you need 6 times more renewable electricity to heat the UK's homes with hydrogen than you need to heat it with heat pumps. And that 6 times is just an insane amount of renewables. So it really isn't going to happen for home heating, and it's not going to happen for trucking. So hydrogen will be used for making fertilizer and maybe making steel, possibly.
It's quite interesting looking at research not so long ago, because the only hydrogen here that I could find was actually grey hydrogen.
Yeah.
And when people were saying the great advantages of ever using it, of course, didn't go through the fact that it all came from petrochem plants.
That's right.
And there was a greater amount of CO2 given off in the preparation and delivery of that hydrogen than there was using a standard petrochem.
Exactly.
So if you build a bunch of hydrogen buses and then you run them on grey hydrogen instead of green hydrogen, so that's hydrogen made from methane, the emissions are way worse than if you just left it all alone and ran them on diesel. You better just not do anything, run on diesel. The last thing you want to do is promote use of hydrogen vehicles and then run them on dirty hydrogen. It's the worst thing you can do.
Is there any manufacture at the moment of green hydrogen in this country?
There's little bits. There's little bits.
Small.
Just I mean, there's a whole electrolyzer industry which is spinning up, but they
I've
don't.
seen diagrams of wind generators and then electrolysis and how they're going to make it work and so on. But what fascinated me when I was doing that research at that time as well was the fact that I think when I looked at it on average of between 8 and 11 days a year, there's no wind power.
Well, that's a problem. That's a problem in itself, and there's a storage issue, the energy storage issue.
The other thing which is absolutely fascinating is that with the national grid at the moment, trying to, some very large schemes I've been involved in, they're talking about using heat pumps and so on. They're talking about up to 20 years of providing getting the infrastructure into place right now. So huge limitations there. And it's very interesting that these things are spun in a way with the government that you're almost there. We certainly are not, because I know for a fact with power generation, there's a huge problem still today with frequency control of wind generators and frequency control of photovoltaics. And at this moment in this country, if you look on Grid Watch, I think you'll see every day on average about 45% of the power generated in this country comes from combined cycle gas turbine plants. And because of the problem with frequency control, they have to keep the gas turbine plants running 24/7 in many instances, just as spinning reserve to hold the frequency.
Yeah. Well, there are a set of problems there around storage and control, which do need to be solved. Australia's doing very well. You know, South Australia, they're doing very well running on wind and solar, and solving. You know, gradually these problems are being solved around the world with various different technologies. Yeah.
Just with the electrification of the overhead wires on the roads, where do you see that happening? I was just thinking about my trip on the weekend to Birmingham on the motorway, on these up and down roads that are uneven at high speed. And if you had vehicles like, how do you see the system working?
Well, there's two possibilities. As I say, one is overhead contact lines, and the other is conductors in the road. Both very interesting. The overhead contact lines, there are three demonstration projects on motorways in Germany, 5 or 10 kilometers at a stretch. So the technology works very well. It may be that you need to maintain the surface a bit better than some UK roads. That's fair enough. It would be in the truck lane, in the left-hand lane. And it would be on the most heavily populated roads. So I showed that network, the light network there. That's where you'd start. So
They stay in the one lane.
stay in the one lane. The trucks all live in that lane most of the time anyway. They can drop the pantograph and pass as they do now. So it doesn't make any difference to the traffic. If you have the strips in the conductors in the road surface, cars could charge on those as well. So it would be possible to have those in more than one lane. That would take all the batteries and all the cars down in size. So the thing about the overhead contact lines is that it's privately financeable easily, right? You can sell enough electricity on the main motorways to the trucks that are going past to pay for your infrastructure investment without any real difficulty over a 15, 20 year typical infrastructure investment period. And the reason that you can do that is because it's so much more efficient than existing diesel vehicles. The energy costs are so much less. It gives it that headroom for paying back the infrastructure, and in fact for paying tax, to replace diesel excise duty. So it's perfectly doable by private finance. It's highly economically attractive, all because of the efficiency savings. But you start off with those main roads, which are heavily trafficked.
Drive at high speed. It's just the unevenness and the practice of those things.
They're all right. Yeah, that they can manage that. Trucks don't go faster than 90 kilometres an hour.
David, as a thin wire electronic engineer, I found this fascinating. One thing you didn't mention was wireless charging. Now, I'm an optimist. I know that there's probably huge issues with efficiency, but I'm an optimist. Let's assume that we can solve that. Is wireless an option for static charging when they're at rest, or like you've got in the road? I was writing about, there was a trial in Detroit where they actually have got wireless induction charging.
Wireless. I think one thing we have to assume is that people are only going to pay for one charging system, right? So if you're going to have it underneath the truck, it's going to have to do everything for you. You're not going to have a static charger underneath the truck and a dynamic charger above the truck. So I reckon that's probably true. Contactless wireless charging works well for static charging. There was a trial in Milton Keynes a few years ago. Bunch of Milton Keynes buses, opportunity charging at each end of the line with wireless chargers. In that case, they had these little sort of frames which they dropped down to minimize. So the air gap is really important, right? You need to minimize the air gap. So they dropped their pickup down like your electric toothbrush, and that worked a treat. Worked really very well. Once you get to and they were charging about 50 kilowatts. So a inductive loop can charge at about 50 kilowatts, which is not bad. Now the problem is that in the truck you need to charge at 150 kilowatts at least, and you need another 150 kilowatts to drive the vehicle. You need 300 kilowatts. So that's either 6 inductive chargers. Well, it is 6 inductive charges continuously, right? So what that means is that your inductive loops in the road are every 1 or 2 meters. Early in my career, I did a lot of work on traffic instrumentation. And we used to cut slots in the road and put sensors in the road for weighing trucks and so on. And what you discover is that when you try and stick things in the road, they are subject to the most horrendous environment, right? Freeze thaw, hot, cold. It goes from 80 degrees on a hot day to minus 10 on a cold day. And everything gets pounded by 10,000 10-ton axles a day. And so that's a really tough environment for anyone to design anything for. Now you can imagine that if you had an inductive loop cut into your road every meter, getting hammered by that it would be a bit of a problem. You'd have a bit of a maintenance problem. So just for that reason, I don't think that can work, just because of the maintenance issue associated with inductive wireless charging. I don't see that as being a viable route. The other one, where you've got the conductive strip up the middle of the road, I think has got a better chance. It's still got the same problem of the environment and salt water, right? In winter, you've got very high concentration of salt, so that's a challenge as well. It's a very tough environment right on the road surface. The advantage you've got down the middle of the lane is that you don't have the axles pounding it. You only just have occasional vehicles passing, crossing over the lane. So that gives it a better chance, and you have a continuous cut down the road rather than lots of discrete cuts that cause stress concentrations and so on. So I think that the contact strips in the road have a fair chance. It's a lot better. I have to say, I was very skeptical. I went and visited them in Sweden a month ago, and I was quite impressed. It was a lot better than I expected, a lot better. And I think that it does have a real possibility.
Children touching them. Yeah.
Well, the way it works is that it has pairs. They have strips which are about so long, I don't know, 750 long, alternating, and they alternate plus minus, plus minus, plus minus. They have a microprocessor every 3, which switches them on and off. So they're only on when the vehicle's over the top. So for a child to touch it,
It's already been killed.
Yeah, he's lying on the road underneath the truck. Well, I mean, it's possible if you had stationary traffic and somebody threw the ball on the road in the traffic jam and it went underneath the vehicle, you can imagine situations where it could be dangerous. But on the whole, it's not, and it's automatically switched, and there's no vehicle, there's no power.
What kind of voltages are you talking about? Under
So for overhead contact lines, they currently run, they're trying to go up to 1500 volts. So they're like trams. It's tram technology rather than train technology, right? Trains run at 25 kilovolts AC. The trams run at 1200 or maybe 1500 DC, and so that's the technology is tram technology, trolley bus technology, rather than trains.
or the strip in the road?
They're talking about the same kind of thing, 750 volts, I think was what they said. I mean, there are some interesting challenges. If you've got a road covered in salt water and contacts at 750 volts, it's a non-trivial situation.
About at the power end.
Yeah.
Might be the last question. That's you, Leo.
It sounds like all pieces of air, and we're not talking about the distant future, we're talking about
that. And we know that we have some bad actors who are trying to stop the future from happening until a distant future. And we've got the government who can maybe kickstart things. When can this happen? Not will, but when can this happen? And there is money to be made. And somebody's stopping the train from leaving the station.
Well, that's not exactly. So there's a big movement on battery electric trucks at the moment. There's a whole bunch of studies going on. Department of Transport put in 140 million into studies. We're running a project which is interesting. It's a lot of R&D and trying to sort of chivvy along the battery electric industry. At this point, people don't understand what I've just showed you, right? The government thinks that all they have to do is put a few charge points into motorway services, and it's just not. So when you look at the thing from the logistics point of view, the logistics industry doesn't know how it's going to do it. The government is deluding itself. So that's the current starting point. And the third dynamic, which is important, is that National Highways absolutely doesn't want overhead contact lines. They don't want it. And the dynamic here is, the Department of Transport says, okay, these guys say overhead contact lines are good. We better ask National Highways. They ask National Highways. National Highways says, nah, we don't think it's a very good idea. We don't like that idea, sorry. Now, National Highways are the experts, right? They're the highways, they're the gurus. They know all about safety on the highways. And once they say, we don't like the idea, it's very hard to get anything to happen. So that's a function of our democratic system. So you've got the environment on this side saying, we have to have dynamic charging. You've got National Highways saying no. Now, how do you do anything about that? You have to have someone with a big, bloody great boot say, yes, you bloody well will, National Highways, because the environment says we have to do it. Well, that, where do you see that? If we look at the shape of government, that isn't about to happen. I think that the lever that can be pulled is the grid, the electricity connections. I think that the powerful player in all this is the electricity industry and the set of distribution network operators and so on, the national grid, that have to provide the electricity infrastructure. Because when you look at that analysis, there's 30,000 warehouses in the country, that need grid connections for charging. If you go for a battery electric solution, you've got 30,000 warehouses that need big fat grid connections. And we're not talking about little grid connections. We're talking about, 10, 15, 20, 25 megawatt grid connections, enough power to power a town, small town. So they're big connections, and the electricity companies can't possibly supply that. They've already got a 4-year waiting list if you want to put a bigger connection in to charge a couple of taxis. So I think the combination of the logistics industry saying, look, we've looked into this, we can't carry our heavy loads, we can't charge because we've got to put these really expensive connections into our warehouses. The electricity industry saying we can't possibly support all those electricity connections. The solution, the electric road solution, the dynamic charging, will involve about 100 grid connections at strategic points. That's much more doable. A single contract to just go through and cut slots along the road and drop these things in, put charging units up the side of the motorway. It's a straightforward thing to do, much more easy thing to do than putting those fast chargers, 50 loading bays in 30,000 warehouses, which is a really big problem. So I think that the answer is that the electricity industry ultimately trumps national highways, or a combination of electricity and the logistics industry. Ultimately, they say, actually, we can't do it that way, the way you think it just will not work. We have to have dynamic charging because of these issues. So I think that's what will happen. But in the meantime, there is a fair bit of momentum building battery electric trucks and starting to install some static chargers on simple routes, simple shuttle routes, 100 kilometers backwards and forwards, that kind of thing.
Sorry, you mentioned that the electricity generation companies should lead the way, but should it not be the people who are driving them around lead the way? For example, your retailers who are using the distribution networks, could they fund the infrastructure? And also earlier when you mentioned that they need their warehouse power supply, could they not perhaps look into diversifying into power generation at their warehouse sites? For example, solar panels on their massive roofs.
All good, very good questions. So if I take them back in reverse, you can put solar panels on the roof and you can power the fridges in the warehouse, in a refrigerated warehouse, for example. Pretty good. To power the trucks, you're talking about an order of magnitude more power. I've got one partner who runs trucks in East Anglia, and he's got a bunch of properties. And I showed him this and he said, perhaps I should fill my farm with solar panels and move my trucks to, right? And what he was saying was, perhaps I should become an energy supplier. Perhaps the logistics industry should become the energy industry or energy supplier. And there is, some strong truth in that. The real challenge for the electric roads, the dynamic charging thing, is that you have to have a level of consensus at a government level, and you have to have a way of the funding. The funding problem is like any infrastructure project. You're going to build a big bridge. It's going to take you 10 years to build the bridge, and before you start collecting, from start to finish. And you're going to need money all that time. You don't generate any revenue for your investors, and you need to have, it's 10 years before you start to collect the toll. And it's the same here with the electric road system. You got to spend 5 years investment building the thing, and you've got to wait for the traffic to build up, and then after 10 years, you start to sell enough electricity to pay off your debt. But you have to have finance for that 10 years. And the way that you do that is in an infrastructure project is the government gets involved, and it gives, for example, you use a RAB model, or the sort of model where the government pays back the interest early on, and ultimately it breaks even. You have to guarantee demand. Build Hinkley Point, right? You can only build Hinkley Point by the government saying we will buy electricity from you at this price, this strike price, forevermore if you build this for us. And so you have to have some guarantees in place to get investors to put in billions of pounds that you need.
Enough guarantee already? Is presentation not enough evidence?
Well, not for people to put in billions of dollars or pounds of money.
Your consortiums and centres for sustainable transport, and they're all signed on with all these big corporations.
Yeah, you need Macquarie Bank to come in with 20 billion, and they're only going to do that if they know there's zero risk, and so guaranteed conditions. So you ultimately need the government to lubricate, not to subsidise, but to lubricate the process, that long-term funding that you need, which you do on any infrastructure project. And so that's the challenge, is to persuade them. And I think it's this combination of the logistics industry and the electricity industry, which together we need to mobilise to persuade government.
Is there the potential to do something like
Silvertown Tunnel, where it's a PPI? So they, and Macquarie Bank are one of the backers of the Silvertown Tunnel. So
yeah, but there must be some. I don't know how that financing works, but there must be some guaranteed income at the end. Otherwise, Macquarie wouldn't. That's right.
I mean, there's the tolls on the Silverway Tunnel Road. So that, I mean, if you're going to sell the power back to the trucks, then
that's right. No, it's perfect. It is absolutely privately financeable in exactly the same sort of way.
I mean, we're constantly digging up the highways, so to whack something in while we're doing it. I mean, I work for Bad Nuttall, so we're building Hinkley Point, so we know that. We're constantly digging up the highways and the Silvertown Tunnel, so there's definitely some options there.
Yeah. Good.
I want to say thank you again. It's been a very informative talk. I think everybody in this room, everybody watching the video, is more informed than the government, and you have a better population. And we are all engineers. We shouldn't be just talking to ourselves. We should be talking out to a wide population, and that's part of Tech Talks that we're doing. So, thank you very much, and thank you very much.
Good.
Also, I'd just like to present a bottle of Shiraz from.
Very good. Thank you.
If you enjoy it.
Yes, terrific. Excellent. Very good, from Barossa Valley. I'll enjoy that. Thank you. Terrific.
Tech Talk next Wednesday. It's part of our AGM, but you don't have to come along to the AGM when you're not interested. It's Prof Davies is going to do a talk on geotechnical research and what outcomes of that are leading into sustainability and various areas.
I've already got a ticket, so I'll be there. So everybody.
I've sent out an email to a few of you, but hopefully we'll get it through the usual sources of the invite. And yeah, please do attend.
I'll put in a plug for Rosie Barnes in June. Rosie's a friend of mine. She's great. So well worth listening to.
And we're very lucky to have Rosie agree to give the talk. She's and well, we'll talk about her in the next event. But yeah, thank you.
Fantastic. Yeah.
it's a little bit more